Okay, good evening everybody. My name is Fergal Cahill and I am the Secretary of the Structures and Construction Division here. This is a joint lecture. It's hosted between ourselves and also the Irish branch of the Institution of Structural Engineers. So I just want to welcome you all here this evening. I suppose the first thing, just a little bit of housekeeping, the fire exits. There's the main fire exit is the door that you came in behind you, and then also there's another fire exit down here to your right. And then if you could just turn your mobile phones to silent for the next hour or so, that would be really appreciated. So our lecture this evening is maintenance of the Forth Road Bridge. Most of you will be familiar with it. It's an iconic suspension bridge in Scotland, and when it opened in 1964 with a main span of 1,006 metres, it was the fourth largest main span in the world and the largest outside the US. And it just recently celebrated its 50th anniversary in 2014, and I believe it carries about 25 million vehicles a year, so it really is a vital link in Scotland's road network. Some of the interesting things, I suppose, with cable supported structures would be that I suppose those who fund their initial construction costs may not be aware of how much it costs in terms of their life cycle maintenance. And secondly, those who operate and maintain them, there's a lot of lessons that can be learned from operating and maintaining them, don't necessarily get translated into new design and construction. And our speaker this evening is Barry Colford, and I believe he's going to touch on those two items, but also, I suppose, the major interventions that they have had to do on the Forth Road Bridge over the last 10 or 15 years to ensure its structural integrity for its remaining lifespan. So in terms, our speaker tonight is Barry Colford. Barry is a chartered civil engineer by profession and is a fellow of the Institute of Civil Engineers in the UK. Barry is author of a number of technical papers on bridge engineering and is a European Committee member of the International Cable Supported Bridge Operators Association. He represents the Longspan Bridges Group on both the UK Bridges Board and the UK Bridge Owners Forum. Academically, Barry is involved with both Edinburgh University and Edinburgh Napier University in their MEng and MSc courses, and he is, of course, the Chief Engineer and Bridgemaster of the Forth Road Bridge in Scotland. So I'll just hand over to Barry now.
Well, good evening, everyone, and thank you for turning out on this lovely March evening. It looked a great night for a walk around the park, but thank you for coming anyway. I'll give you a talk tonight on some of the issues that have come about on Forth Road Bridge over the years. There'll be nothing too technical or heavy in it. Hopefully you'll have plenty of questions that you want to ask at the end. Fergus touched on the subject of maintenance, and it is true that I think at the procurement stage we forget about the costs later on down the line. We're getting really much better at designing for construction, but we're still not really that good at designing for maintenance. And it's an issue that keeps cropping up. Those of us who are involved in maintaining these structures try to keep pushing the issue. Where did Longspan Bridge engineering begin? Well, there are contentious thoughts amongst various people, engineers, about where it did all began. I think it began here in New York City with the opening of Brooklyn Bridge in 1883 with a main span of 486 metres. This was a phenomenal piece of engineering at a time not too long after the American Civil War had ended. And this is a view looking from New York City onto Brooklyn here, and that's they're affectionately known as BMW, Brooklyn, Manhattan and Williamsburg bridges. And this is crossing the East River. Before, and this is what big bridges do, they both act as a strategic route and help commerce and help a nation develop, but they also join communities. This bridge was actually instrumental in forming the metropolis, which is known as New York City now, because it brought Brooklyn City, which is a completely separate city, into the fold, with consolidated into New York in the late 1890s. And without the bridge, it probably wouldn't have happened, or perhaps we should say the bridge kick-started it or made it happen. The interesting thing about Brooklyn is that it was the first use of high tensile wire and it made this long span possible. If you compare it with Clifton Suspension Bridge, which is 214 metres, that's a fantastic leap to build something like this, to design and build it. Of course, this is perhaps the most famous long span bridge in the world. This is now 1937. This is not too far away from Brooklyn, within 50 years. And this is a 1280 metre span. And that was another great leap of faith by the engineers who designed it. It's been retrofitted quite a bit for earthquake engineering, but apart from that, it is still functioning as it was intended after opening in 1937. This actually should be the most famous bridge in the world, but it isn't. It's the Akashi Kaiko Bridge in Japan, and it's got a main span of 1,991 metres. That's almost 2 kilometres between those two big towers. And if you ever are lucky enough to get to Japan, it's really worth a visit. It's a monster. This slide doesn't do it justice. It's twice the length of Forth Road Bridge between the towers, and it's quite a sight. Those are suspension bridges. Of course, cable-stayed bridges are being built as well throughout the world, and this is another development. There seems to be that cable-stayed bridges spans are increasing as well, and I'll show you a graph of that in a bit, but this is Stonecutters in Hong Kong, 1018 metres. We're now over 1,000 metres for cable-stayed spans, and 15 years ago that wouldn't have seemed possible. There are lots of them being built in China. This is one across Yangtze at Wuhan, and it's about 500 metre span. There are dozens of these built and opened in the past 10 to 15 years in China. The big question is, how well have they been built for maintenance? And the answer, I think honestly, is probably not very well. And there may be an issue, like any developing economy, the race is to get the infrastructure put in place, to get the capital flowing, to develop the economy. Sometimes the thought of maintaining them afterwards is kind of a secondary or even a tertiary one. And a lot of issues, I think, are going to crop up over the next 10 to 15 years with these bridges. Still building suspension bridges in China as well. This is one which has just recently been completed and will be open in April of this year at Wuhan. This is quite a beast, this thing. It's a 3-tower twin-span suspension bridge, which is pretty unusual. And the 2 towers at the ends are concrete, and this one's steel to allow it to flex when there's asymmetric loading in the spans. Building suspension bridges is actually pretty easy, relatively easy if you know what you're doing. You build the anchorages, you build the towers, you spin the cables, you drop your hangers, and then you build the deck off of them. There's a lot of issues over cable-supported bridges versus suspension bridges. What's the best form? Suspension bridges cost about £5,000 a square metre to build. Cable-stayed bridges will be about £3,000 a square metre. So there is and it's mainly on construction cost and construction time that cost is realised or shown. Here's a graph of developments and spans over the years. Here's a friend here in Brooklyn, back in 1880, and you can see what's happened. These are suspension bridges. This massive jump here, George Washington and Golden Gate, and then it flattens off again, and there's Akashi. The poor Danes here built Storebelt in the same year, 1,600 odd metre span, and get gazumped by this monster. So they didn't hold the title for very long at all. What will happen after that? Who knows? 3-kilometre span to Messina. It has been on the cards for a while, but hasn't developed. And we've got, if you look at the shape of this, it's shifted to the right because of the time, and it's also down because of spans. But this is cable-stayed bridges, and they're very similar in shape. This jump here to Pont de Normandie was huge. This was Michel Verlogeau's great leap in the dark, because they were pottering around about 500 metres, and he built one at 856 metres. And again, it's jumped up, and we've had Ruskey Bridge just opened 2013, 212-13, with 1,104 metre span. So it's quite a jump there. concentrating on suspension bridges, they are very complex, highly non-redundant structures, and by that I mean if one of the major elements fails, then you've lost the bridge. There's not many places for load to go. They're usually critical links within a nation's infrastructure, so maintaining them is vital, especially, and we're all facing costs being, so you've got to justify the maintenance costs in the future. This is a video of how the bridge actually works. It's speeded up, of course, but it just shows you how lively and flexible the structure is. This is on a fairly lightly loaded day with the wind not doing very much. The bridge will actually move it will deflect 4 meters when it has its full loading on it, its full traffic loading on it. And it will move 7 meters laterally when its full design wind speed is hitting the bridge. We've got GNSS sensors on the bridge, and when we got hit by an 85 miles an hour gust the other month, the bridge moved 3.5 meters to the side. So it does, these are very flexible structures, and they're also highly non-redundant structures. And they have to be looked after. There's a lot of money needs to be spent on them, because you don't want to end up with something like this. This is Kartanegara in Indonesia. It failed a few years ago. Now, whether it was design, construction, inspection, or maintenance that caused the failure, we don't know. I'm not sure we'll ever know. But lives are lost, and we can't afford that for that to happen. But it's not only in so-called third world countries that we get problems with bridge maintenance. This is a bridge in the United States across the Ohio River. It's Fort Steuben, and it deteriorated to the point that it had to be demolished, and a new one was built. I think that's a terrible state for you to let your nation's bridge stock to get into, that you have to do that. But that's just a personal view, of course. Going back to our old friend in Brooklyn, which is actually quite an unusual design, because John Roeblings was a fantastic engineer. This is actually a hybrid. It's a suspension bridge with stays on it. You can see the stays here. And actually, there's a third Bosphorus being built at the moment by Michel Verlageau's designing it, who designed Pont de Normandie. And he's adopting what Roeblings did here. There's full railway loading in the bridge, and it's over 1,400 metre span. Suspension bridge, and he's putting stays on to give it some stiffness in the system. And he's copied, he's quite open about it, he's copied what John Roeblings did in Brooklyn. Functionality changes over the years in these bridges as well, and we must be aware of that. The top section shows Brooklyn opened in 1883, and Roeblings would probably never have thought that it would be taking motorised vehicles nowadays. And you see to 1944, and with some structural alteration, it's now carrying vehicular traffic only. The pedestrians are in the same place, but it's restricted to only light vehicles and cars. Golden Gate, that's probably the heaviest loading that it's ever had, probably 4.5 to 5 kilonewtons per metre squared. Crowd loading there, probably greater than the heaviest traffic loading that it's had. I'll talk a bit about Forth Road Bridge itself, because it's a structure that I've been involved with. This is an interesting shot. The bridge acts, as Fergal said, it's 25 million vehicles a day cross. Now the diversion route is huge. It's around by Kincardine. It's 22 miles there and 22 miles back. If we are unlucky enough to have an incident on the bridge, it's 2 lanes north, 2 lanes south, as we did when we had a diesel spill and we had a lane out for 6.5 to 7 hours. The queue length was 4 hours coming out of Edinburgh. Now, there was no point in people going around by Kincardine, because it would have taken the same time. That sort of thing becomes politically a problem, and we get a lot of pressure when that happens. So we are very restricted in what we can do. We can't close a lane during the day or a carriageway during the day. Most of the work is carried out overnight. Or if we have to resurface on specified, notified well in advance on carriageway closures on weekends when traffic's down about 10%, but we still get 2.5 to 3 hour queues when that happens. This is a bespoke platform we used for painting the towers. This is a dropped object canopy, which was erected, temporary canopy erected here in case anything fell out of that. If someone dropped a 7.5 kilo paint pot from there, then that would be a bit of an issue for us. So we felt we had to build this dropped object canopy here. And the platform itself, when it moves down past the bracing, we have to lift panels off the floor and put them back down, and lift them off and put them back down. Now they were tied off with lanyards, and if you go up and watch the guys doing it, they'll tie the lanyard on, tie it off, put it on. They'll do that once. When they do it 100 times or 200 times, sooner or later they're going to forget to do something, and then you have an accident happening. We couldn't afford that to be the case, so we built this dropped object canopy. As a result, the cost of painting those towers was about £500 a square metre. There's 17,000 square metres in the towers. Of that £500 a square metre, £7 was paint. Most of it was access and containment. So that's the issues. We're not allowed to have anything going into the Forth. It's a site of special scientific, it's a triple SI. Really special scientific interest, I think it's called. Loading has changed as well, of course, over the years, as we know. Up in the left-hand side, that's the load per kilonewtons per metre. On the bottom is loaded length. The blue line is the design load that you probably designed Forth Road Bridge for now and what the new bridge will be designed for. The green line is what it was designed for back in the 1950s when the engineers were designing it. You can see it goes from just over 5 kilonewtons per metre run to something like 17. The green, the purple and the red lines are our BSAL lines. We adopt a bridge-specific loading using a weigh and motion station, and it hasn't changed much since 2002. But you can see how much load has increased. But the issue is that, in actual fact, live loading on some of the elements, the cable elements, isn't a big proportion of the load. 85% of the load in the cable, for example, is dead load and super dead load. So increases in live load don't make a tremendous difference to some of the elements. They do to the deck, which is carrying the load to the cable system. But the cable system itself is working hard all of the time because most of the load is there all of the time. With maintenance in these suspension bridges and any cable supported bridge, the big ticket item is the cable system and anchorages, if you've got them. We've also got the three usual suspects, which everyone has, no matter what the bridge is: corrosion of steelwork, waterproofing and surfacing, and our old favourites of bearings and joints, the ones we know and love. This is a list of the works that have been carried out in Forth Road Bridge over the years. Quite significant amount, most of it improvements to the bridge. Some of it changes due to change in loading, some of it changes due to change in risk. For example, we had to build pier defences round the bottom of the piers because shipping has changed, and the overhang of the bows of modern day vessels would now impact on the steel tower legs, whereas before, when they designed it, that wasn't thought about because they wouldn't have. So there's a lot of money has been spent on the bridge over the years, and I'm going to concentrate on the cable issues that we've had. But interestingly, the biggest amount of money that we've spent, the greatest amount of money has been in replacing the viaduct bearings. The approach viaducts are very common, two simple box girders with a concrete deck on top. And there's about 750 metres of viaducts in total, 450 in the north, just over 260, 270 in the south, in the north, and 450 in the south. And that's been the biggest ticket that job in cost terms. We jacked the box girders up and replaced all the bearings, but we had issues with chlorides in the piers that were supporting it. But I will concentrate on the cable works that we've carried out because they've caused quite a lot of interest over the years. But that's just an idea of the money spent. We've spent £259 million on capital projects since the bridge was opened. Now, the cost of building the bridge, now these costs are costs as of the time of spend. The cost of building the bridge was £11.5 million. And that's not too unusual. George Washington Bridge is just about to undergo a $1 billion refit, in addition to the money that's been spent on it to date. You've got to spend money in these assets because things change, risks changes, loading changes, and things deteriorate as well, because they do move about quite a bit. I'll look at the cable in some detail. Cables and suspension bridges are fairly unique in that they're made up of individual wires, and this is the same sort of, this is how Forth Road Bridge cable was formed, and that was how Roebling's formed Brooklyn, and Golden Gate was formed, and George Washington, and all the bridges up to that point. And it's interesting because these wires are high tensile galvanized wires, and they come in reels onto the site, and I've seen other photographs how they put them, how they actually coax them, I think is the best word, into place, and it usually is with pinch bars. Now, as you know, if you're using a pinch bar and a galvanized wire, then you will damage the galvanizing. So, as in all cases, it's what happens on site that sometimes has the greatest effect in how your component will act throughout its life. There's been a development new development in that these are called strands, and there are 37 of these, and the cable is put into strands as it's spun. The Japanese come up with a new development where they are now forming the strands in the factory, and that takes away splicing, and it also means you're building them or constructing them in a factory setting. It means you have to transport them in huge drums, but it has assisted both in speed and in damage. It helps prevent damage to the wire when it's getting put in place. The wire specification for these high tensile wires is very, very high. You can see in very old units it's 100 to 110 tons per square inch. In the units that I'm used to, it's about 1600 newtons per millimetre squared, which I believe these days is a megapascal or something. I don't know, about that anyway. But when you think of the steels that you're using for designing normal structural steels, for high strength structural steels, compared to 345, compared to these are very high tensile wire, and they're galvanized and then placed in the cable. You then compact them, and traditionally that's a compacting machine. As you can see, the guys are not posing at all in that photograph, which was taken sometime in about 1962, 63. And then what happens after that is there's a galvanized wire wrapped around the outside under a bit of tension by a wrapping machine, and you can see it on the right hand side. Before the wire is wrapped around, it's been traditional to wrap it or put red lead paste on it, and this was a Roebling's idea, and then put the galvanized wrapping wire around. We tend to use zinc paste now because red lead is of course kind of banned from use. And that method of construction has been used since Brooklyn. You can compact the cable as much as you like, but you'll never compact it to take all the voids out of it, because you've got circular wires touching each other. Mainly, the average compaction will take you down to about 20% voids. So even though that looks a very dense cable, 20% of it still is void, is air. And that's what it looks like in section. Galvanized wire, wrapping wire, red lead paste here or zinc paste, wrapping wire here, and coating. Japanese have developed S wire instead of round wire to try and help keep water out of cables, because this is what was found in some of the American cables back in the 1990s. Despite all of that protection, the Americans started opening up their cables and finding significant damage. Now, that does look pretty bad, and it is, and it's actually relatively easy to open up a cable obviously at the bottom level of the thing. You take the wrapping wire off and you drive wedges into it to open it. And they were finding really serious problems in some of the bridges. And because of that, the National Academy set up a working group to look at producing guidelines to inspect these cables, because nothing was available at the time, and to evaluate the strength of them. Once you've inspected them, what do you do once you find out the conditions like that? How do you evaluate the strength or strength loss? We decided in 2004, having gone across to see these things, to have a look inside the cable at Forth, and even though we didn't have water running out of our cable, which they did in some of the bridges, it was dry, it looked great on the outside, it had been well maintained, well painted, but we asked ourselves the question, this is the most important element of the whole bridge. How do we, when we carry out a principal inspection, how can we say that we've had a close visual inspection of the wires within the cable? And the answer is we couldn't. Because it's lead, there's all sorts of issues with protection and health matters, and we've got to take cognizance of that. So we opened up a panel between the hangars, which are about 18 metres, and as I say, it's relatively easy to do here. It's a bit more difficult up there. And this is a bespoke platform that we had to design, build, lift in overnight, and pull it up with turfers up to the top. And then it had to be dropped, moved along, and up to the next panel that we're going to look at. And it's 18 metres between the hangars and Forth Road Bridge. That's how you open it up. You get a small brass chisel, and you just chap it into the wires, and then you get the biggest guy you can find, or the biggest hammer you can find, with plastic wedges or wooden hardwood wedges, and you knock them in. And you can see you actually get right into the heart of the cable. When you do that, the Americans were doing it all the way around. We were a bit more cautious and decided we'd do one sector at a time. You can see that red there is actually the red lead, and unfortunately the first sign that we looked at was when we touched the red lead, it just fell off. It was so friable. But we did expect, or I had expected, that we'd open up this panel at the bottom here, the easy one. We'd see how good it was inside. We'd think, that's great, we've seen it, wrap it up, move along. Unfortunately, we found this. Not as bad as the American experience, but wires falling out, quite damp underneath the cable, quite a bit of corrosion, as you can see. And that's a sort of typical damp, pitting corrosion that we were finding within the cable. This, of course, set off all sorts of alarm bells about crossing the Forth, and as a result of this, directly as a result of this, the government decided they'd have to build a new bridge across the Forth, because they asked for an unconditional guarantee, and I said I couldn't give that about strength loss, and therefore we decided they'd need to build a new crossing because it's such a vital Scotland's road network. We need it, frankly, because of the traffic volumes, but you're not allowed to say that, so better not. We've got other issues with maintenance as well, and the joints in the carriageway, which we're not able to do because we can't close the carriageway for any period of time to do it. So you need a new bridge to be able to free up the existing crossing to maintain it. These are the stages of corrosion that the American guidelines showed. This is fairly new. Most of the galvanizing is intact, most of it is gone. You're starting at 20 to 30% corrosion on the surface. This is stage 3. Stage 2, stage 1, and this is stage 4. Looks really bad. The problem is with the NCHRP, as it's called, National Academy's guidelines, is that it's done on a visual basis. And when you open up your cable, you'll get a wire that looks like that for a metre, and then it looks like that for the rest of the thing, and sometimes it looks like that. Sometimes it looks like that on one side of the wire, and that on the other side of the wire. And that's a great difficulty with the methodology, unfortunately. This is a representation of a slice through which was developed in the guidelines to show the sort of levels of corrosion. Now, red is bad, unfortunately. This is taken from Forth Road Bridge. Red is bad. This is not what we expected. Black, there's no black on it. Again, unfortunately, there's no good stuff. We expected that to be mainly green, mainly stage 2. But the funny thing is that if you look at the right-hand side, there are very few broken wires, lots of corrosion, but very few wires are broken because of that. The wires that did break, they all break like this. This is the case of all bridges that I've seen, except for Williamsburg in New York, where the wire isn't galvanized and it has necked. This isn't a ductile failure, this is a brittle failure. A crack develops, and we don't know why the crack develops at a particular location. Crack develops, the wire in Forth's case is under about 1.25 tons of load most of the time, and as soon as the crack gets to a certain cross-sectional depth, the wire fractures and a brittle failure. Now, it doesn't mean to say you lose the wire. Because of the friction in the cable, it actually redevelops its strength a couple of panels along, but the problem is you can't rely on that forever if you've got a lot more broken wires than just the one, of course, and that's the problem. We took you can take samples. The only thing about taking samples, you've got to splice in, and you can only get them as far as you can cut it with these cutters here, and you've got to splice it in, which again leaves gaps, and when you wrap the cable you can see some of the splices, which gives you a water issue, a path for water. One of the big challenges for us was, having seen the condition, how do you determine how much strength you've lost based on a condition and testing wires? But it's all about cracking. Corrosion isn't the major issue. The issue is cracking. Cracking leads to breakages, which leads to strength loss. There are quite a number of models for calculating cable strength. All are based on sampling and testing. And what we want to know is, what's the current strength and what's the future strength, which isn't an easy thing to do. The sampling is so small in these. That first investigation of ours cost something like £5 million. And I think we did about 4% of the bridge. We opened up 4% of the panels, which isn't 4% of the length of wire. It's length of wire that we looked at was less than 1%. So we're having to make quite significant decisions based on a very small sample, which we're hoping represents the population as a whole in the cable. And these are the sort of errors that you get. So if you can open up 16% of your panels, it's about 11% error. Now, we only opened up 4. I don't know anyone that's opened up 16% because it's just not affordable. Wire strengths, fortunately and unfortunately, depending which way you want to look at it, have gone up in recent years. And one of the problems is, you can see in this graph from Brooklyn, the stronger the wire is, the more brittle it is. There's always a trade-off in life, and the stronger you make it, the more brittle it becomes. It has to be stronger for the bigger spans to cut down weight, but it becomes more brittle, and in maintenance terms that causes a problem, because we know that hydrogen embrittlement, well, we know now that hydrogen embrittlement starts to become a problem at about 150 kips, or about 1034 newtons per millimetre squared. Now that means that the higher you go, and maybe John Roblings knew something when he had his wire down about that strength. Higher you go, the more prone it is to hydrogen embrittlement, the more prone it is to cracking, the more likely it is that you have to make sure that you don't get water in that cable. And we've not been very good at that, unfortunately. This is quite an interesting graph. These are 2 graphs showing the wire that was tested out of Forth Road Bridge cable. The one on the right acts exactly as a new wire would. You can see this is stress versus strain. You'll probably remember this sort of stuff. Sorry, it's in KSI here, but it was an American lab that did it. But yield here, fails here, pretty flat here, but fails at that point here and yields at that point. And that's a pretty good wire. This is a worse wire, also sampled. As you can see, there's a lot of energy required. The strain energy required to break that wire is the area under the curve here. And it's 4%, it almost reaches elongation of 4%. pretty good. So there's obviously no cracks in this wire. This one's obviously had a crack in it, and it fails less than 0.001% strain at just over 200 KSI. Very little energy required to break that. That, unfortunately, was a stage 2 or 3 wire, and that's a stage 4 wire. So the visual on this is that that's the worst wire, and that isn't. So that is a problem for us and an issue going forward, and we need some more work in this to try and rationalise it, because the problem isn't corrosion, the problem is up here. It's subatomic hydrogen getting into the body of the steel. That's what causes cracking, and that's here. Corrosion is an indicator you've got a problem, but it isn't the reason that the cables are losing strength. Cracking's the reason, and wire breaks. We looked at the start, Fourth Road Bridge at a factor of safety of 2.64 or something in 1964. When we examined the cable, we estimated the strength loss was 8% in 2004. Great curve fitting stuff this, you get 2 points. 40 years apart, fit a curve. We decided that we'd want to keep it above 2. Now this is against ultimate failure, this is not against yield, so if you think about yield, it's probably about 1.75 equivalency. 2 sounded, why 2? Why do you want to keep it above 2? Well, it's a nice round number. That's it, basically. I had a word with a lot of the owners in the States, and whilst no one would pin their colours to the mast except for Bill Moreau up at New York State bridges, he said he wouldn't, I won't do his accent, but he wouldn't run traffic in a suspension bridge with a factor of safety below 2. Sounded good enough to me, and so we plumped for 2. Now our thoughts were, how do we keep this line above 2? How do we flatten out that curve? This was another inspection 2008, and this is the optimistic and pessimistic lines. So how do we keep that above that was the challenge. And the conclusions we reached on all of this was that we had different levels of corrosion. Looked good on the outside, doesn't mean it's good on the inside, and even though you think you're doing well with your maintenance, it doesn't mean to say that you haven't got corrosion on the inside. One of the things you have to do, unfortunately, after each one of these, and one of the reasons it's so expensive, is to recompact it and rewrap it. This was the last, in 2004, we got the last batch of red lead paste from the New Amsterdam works in New Jersey. I think they're still manufacturing it somewhere in China, but I'm not quite sure where. You can see the wrapping well. We had to redesign and build this because the original compactor that you saw in the previous photographs went to Severn, and then it went to Bosphorus, and then it disappeared. So we had to build a new one. We decided that we would fit acoustic monitoring onto the bridge to try and listen for wire breaks. There's still a bit of validation needs to be done in the technology. It's quite new. It can provide an early warning system, but it doesn't certainly mean that you don't have to open up and inspect in the future. That's what acoustic monitoring looks like. Unfortunately, this was a prototype system when we put it in 2006, and the fidelity is up so high you can actually hear seagulls dropping onto the cable. So there's some poor guy in Canada trying to listen for wire breaks in Fourth Road Bridge, and he's hearing seagulls and people coughing as they pass him. So he's getting this massive data and he's trying to identify wire breaks, but they do have a peculiar signal. So what do we do to stop it corroding? We looked at oiling. This is Ben Franklin in Philadelphia. It just doesn't look, you open up the cable and pour oil in it and wrap it up and hope for the best. Doesn't look very good. And I don't understand how it works, because the oil dries out and you have to do it again. It hasn't really caught on. So we looked at dehumidification. If you put a bit of galvanized steel in a chamber with relative humidity below 40%, it will not corrode. But one important thing is that's a bit of steel without any stress in it and without any damage done to it. So we fitted a dehumidification system to the bridge We put an elastomeric wrap round to try and keep the air in. I'm not a great fan of hiding things by putting wraps around them, but in this case we really had to. You can see the system. Green is air in, red is air out, and these are the inlets and outlets. Dehumidification chamber, fans and a dehumidifier, pumping it in at about 3,000 pascals. Very low, that's only about 300 ml of water. Very low pressure, diffuses up the cable. It's supposed to hit a relative humidity gradient. We put inlets there. The Japanese have put them on, started this all back in 1990s by putting it on a couple of bridges, and we've just copied them basically. We opened up the cable by using small wedges, galvanized wedges. And that's an inlet and an outlet chamber there. There's one at the top. Again, getting up there is a problem. I think that scheme cost about £10 million to do. And slowly, and we're measuring, at these outlets, we're measuring pressure, temperature, relative humidity, and flow. When they're working, that is, of course, because the first rule of sensors and anything you put on a main cable is you spend half the time wondering if the thing's working or not. And we think we're slowly, we had another inspection in 2013 and we think it's beginning to level off. I drew this curve myself, and I think you could say it's the optimistic one. Or maybe I just was having an optimistic day. That's a graph of, we're recording cable wire breaks, sort of about 90 wire breaks spread over the two cables equally. The red line is wire breaks since 2006, and the green line is the relative humidity in the east cable. You can see there's 45 wire breaks, there's about 50-50 in each cable. And despite it's been a rocky road with things not working and sensors not working, but there's a definite, we're now down about less than 10% coming out of the sensors, from almost 100% when we started. Whether this is a coincidence that the wire breaks started flattening off when we started dehumidification, I don't think it is. I think I'll point the pointer to that part of the wall. That we need to be about there before we finally say it's working. It'll be about 10 years, I would think. I'll quickly go on to the anchorages because they've been an integral part of the issues with the main cable, because it's all right having a main cable, but you've got to have somewhere to anchor it. These are that's the North Anchorage and Forth Road Bridge. Each of these cables is taking about, dead load is about 12,500 tonnes in each of these cables. Total load is about 13,500 tonnes in any one day. And it's anchored into rock on the north and south sides. Cross sections like this. This is the North Viaduct above the anchorage here in this simplified script here. The tunnel goes down for about 76 metres at an angle of 30 degrees. And it was a fantastic idea. And the engineers at the time in the paper describes it as innovative, which is enough to make anyone's blood run cold. It's post-tensioning in a tunnel. Now we all know what's happened to post-tensioning in bridge decks. So to put it in a tunnel in the late 50s, this was finished in 1961 because you have to build your anchorages before you do anything, was really, really innovative. Post-tensioning in a highly saline environment, because there's mean high water springs here, so it's underwater most of the time as the tide goes up and down. There's an access shaft down here because the post-tensioning was down through ducts and it was tensioned down here, and of course that's now filled in and we can't get anywhere near it. And just to add a bit of spice to the whole thing, the foundations for the viaduct are somewhere above the tunnel. Now it's interesting because we've got a record drawing that shows that footing there, we've got one that shows it down, we've got one that shows it up there. All three of them proudly stamped as built. So the strands are in grouted ducts within the tunnel, and we have no idea of the condition of them. We do know that in the ICE paper which was written, it did say there were some concerns about corrosion of the strand, even before the cable was spun. Hydrogen coming off in the chamber here, and if I go back one, there's the chamber there. These are the anchorage chambers, which we've got quite a lot of security around these, obviously, because they're fairly critical infrastructure. That's the chamber as the cable goes in, and that's That's the chamber there that you can see. And the cable splays out over a saddle here and is looped round strand shoes here, and I'll show you these in a sec. That's a post-tensioning duct. 32 diameter strand. It's a Warrington lay with filler wires, 8 number filler wires, 19 strands, galvanised. And that's the sort of thing that made us worried. You get these spacers, and does the grout go in there? Is the grout going in there with banding round with steel ducts on the outside? And they were grouted from the bottom, which must have been some feat to get grout all the way up. And they did notice on building that they were getting hydrogen coming out into the chamber, and they thought the hydrogen was because of zinc depletion caused by corrosion. That's how the chamber was built, tunneled in there. That's one of the tunnel lifts. And there isn't an issue, of course, with the rock tunnel itself. The factor of safety against that big rock plug pulling out is pretty huge. It's over 3. That's not going anywhere, but unfortunately, as we know, concrete's not very good in tension, and without the post-tensioning, the concrete would pull apart. So post-tensioning is a vital part, obviously, of the system. And it's in these ducts cast into the concrete, in these steel ducts here. And that's a shot of the inside of the Anchorage chamber. That's the top of the steel ducts. They're in sockets here, zinc, hot metal sockets, and they were slid down in the sleeves, down to the bottom, and then they pulled them, jacked them at the bottom, and wedged them. There's 150 tons in each of these socketed tension strands, and there's a big strand shoe at the bottom here, and there's a strand plate which fixes onto the face of the tunnel, which is here. So there's 13,500 tons or so trying to pull that big plug out the ground. The plug won't pull out, and there's all these post-tension wires stopping the concrete pulling apart. And we don't know the condition of them. There's no way of finding out. We tried ultrasonics, radar, everything. No one could guarantee that they could tell us the condition of these. So we've no sign of movement. We're fairly not happy with it, but we accepted that's what we had. But unfortunately, in about 2005-06, we received copies of the resident engineer's reports, which we hadn't had before, from a private source, which painted a somewhat darker picture than the ICE proceedings had. There were great concerns over corrosion in these strands, and they had several reports from corrosion bodies at the time to come and examine them and try and find out what they could do. And one of the things that they came up with was to install pumps round about the chambers and have them running continually to keep the water level below the bottom of the anchorages. And that's how the story ended on these reports. Now, it was quite clear to us that we did try and have a look, but there's never any sign of a pump's ever been installed, either on the north or south side. So we don't know the story, we don't know what happened and why the pumps weren't installed. All we knew was that they had never been there. So that gave us cause for concern, and we decided that we would need to take action to try and establish the structural integrity of these anchorages, because if you lose an anchorage, you not only lose the bridge, there's a possibility you lose the river as well, and that couldn't be allowed to happen. So we decided, seeing as there wasn't any high-tech non-destructive testing method, and that's a picture of the strand shoe at the bottom there in the plate, and there's 6 of these here, and there's about 950 tons holding that in place, and there's about 600 or 700 tons in that strand, those 2 strands trying to pull it out. So we decided, being engineers, best way to do it is just dig a hole and have a look. That sounds like the right idea. So we decided just to do that. Dig a hole behind the chamber on the south side, get down to the top of the tunnel, expose the strands at the top of the tunnel, open the ducts, expose the strands, and have a look. We thought there were going to be 3 possible outcomes. It would be, and 2 of them were easy from an engineering point of view, and 1 was difficult. from a political point of view. The easy ones were it was so bad that the decision would be easy, or it would be so good the decision would be easy. What we thought we would find was somewhere in between, where we'd have a difficult engineering and political decision afterwards. We had really had to take great care over, of course, the foundation for the viaduct here, and this is the chamber. But we decided to dig a hole here and expose the tunnel over this length, and this is about 8 metres down. So all very doable, all very straightforward civil engineering. We're using rock anchors and ground anchors to pin the slopes back and monitor this here to make sure it didn't move. And what we were going to do was a visual inspection, an X-ray. So the idea was to remove the grout, remove the ducts by carefully cutting them, remove the grout by careful blasting, visual inspection, and survey over a length of about 10 metres to 12 metres excavation, maybe a 10 metre, 9.5 metre opening. And this is the Graham's were the contractor who won the job under a quality bidding procedure. 60% quality, 40% cost. You don't want to muck about when you're dealing with the anchorages of a suspension bridge. And this, you can see the foundation there, which turned out to be not quite in any of the as-built drawing locations. Slightly different, but we now know where it is, and we have a proper as-built. As in all things, and again, the as-built drawings showed these to be at a certain height, and they were a metre lower, and they were supposed to be 30 degrees, and they were slightly steeper. All bad news for us, good news for Graham's, of course, but bad news for us. And the concrete in here, this is where the winding gear was, and what you saw one of the original slides where they were spinning the cable was in here. So there was a lot more concrete than we thought there would be. Good news for Graham's again, obviously. And it took it was water jetting and concrete saw cutting that took it out in blocks. That's what the netting's for here. And this was monitored pretty carefully to make sure it wasn't going to kick out and we lose the viaduct. You can see the Forth Bridge in the background here, the rail bridge. So that was, I think it was a £3.5 to £4 million job, again, just to have a look. But we needed to do it. So we found the ducts, and the first piece of good news was the ducts looked in good condition, which I don't know what it meant, but it heartened us a bit. The concrete was incredibly difficult to break out. We thought we were going to deal with Class E or something similar, but it was really difficult. And the other good news is we exposed the first strands and they looked brand new. Now, these have been buried for that long. There's obviously moisture hasn't got into them because they looked in great condition. And just to be sure, we've got some hardwood wedges and teased them apart slightly and found them to be in remarkably good condition. So going back to that, as one of the board members said to me of Forth Road Bridge, Forth Estuary Transport Authority, so you've spent £3.5 million and found out it was okay? Well, the answer was yes, and I could sleep more soundly at night knowing it was okay. I'll just touch on what else is happening in the Forth. You may be aware there's a new bridge being built because of the issues with the cable, and on the existing crossing, the government decided to build the new replacement crossing, which is a cable-stayed bridge, 650-metre main spans. It's quite unusual, and it's a 3-tower arrangement. And the problem with 3-tower cable-stayed bridges is the lack of stiffness in the central tower. Lack of stiffness in the system because of that central tower. It's not anchored back to anything fixed. It's anchored back to a stayed span. And the way it's done, so you've got to introduce stiffness into the system, and you can do it various ways. There's a bridge in Greece called the Rion Antirion, where they've made the towers very stiff by bracing them with permanent concrete angled members at the side, and it looks pretty heavy and bulky. In Hong Kong, Tin Cow Bridge, they've put a big sort of washing line stay longitudinally between the towers and stays at the side. Looks a bit ugly. to be frank. I think they've gone for a really good solution here at Forth. It's a really elegant tower, and what they've done in the middle is cross the stays, and that introduces a significant amount of stiffness into the system. And I think it's a pretty clever idea. These are just some nice images of the construction as it is now, and they're just about to launch the first deck units here. These are the erection derricks here that will be brought in by barge and lifted up. And the first stay is just about ready to go on when the first deck unit's going on, and hopefully that'll start in May. By May next year, the deck will be completed if it goes to programme. These are the approach girders looking from the Edinburgh side towards Fife. And again, these are the approach girders as well. When this is quite an American Bridge are one of the main contractors in this job, and this is an American Bridge detail. It keeps the nose up. Instead of a launching girder, they're using these temporary towers, which are fixed back onto the viaduct, and it's quite clever. So you add bits on at the end and push it out. And these temporary stays here keep the nose up as it goes over the piers. It really is quite clever, and it engendered quite a lot of discussion on locally, because before these towers were built, these were the biggest part of the bridge, the highest part of the bridge. And of course, the comments were, they're rubbish, they don't look anything like, the Forth Road Bridge towers are much chunkier than these. And in actual fact, now that these towers are going up, these are completely dwarfed, and it is a feature of cable-stayed bridges that the towers here the towers at Forth Road Bridge are 100 metres above the deck. These will be 200 metres above, there'll be another 50 metres above the deck. So it's a feature of cable-stayed bridges that they have got to have really high towers. As you imagine, if you have short towers, then it's very inefficient. Stays are usually put in somewhere between 25 and 65 degrees. So you need a tall tower. The longer the span, the taller the tower has to be to hold that up. And at 650 span, that gives you that height of tower. It's normally 0.2 to 0.25 of the span. So it's going to be a fantastic structure when it's built. This is an artist's rendering, and I find this quite amusing because it looks here as if the towers of the new crossing and existing one are just about the same. These are actually 50% higher than these. But and when it's built, you're going to have 3 centuries of civil engineering at Queensferry. This is looking from Fife southward, the rail bridge here, a Forth Road Bridge, 19th, 20th, 21st century engineering. And we have said we're not very good at marketing things in Scotland. In fact, we're pretty poor at it, frankly. But if we can't market this as a tourist attraction, then we might as well pack up our tents and go home. So hopefully we can attract visitors, because it will be a fantastic sight when you see these 3 bridges together in context. I'll stick this one up at the end, shall I? We may be rubbish at rugby, but I'll fly the flag anyway. Okay, folks, that's it. I'm happy to take any questions that you have. I think I'm just about 5 minutes over.
So thanks very much, Barry. That was great. Really interesting lecture. I just want to open it up to the floor, but I suppose if you want to ask a question, if you could just raise your hand, and we'll try and get a mobile speaker to you. And yep. So if anyone's got any questions.
I have to say, during the referendum, I couldn't show that photograph.
Any questions?
I suppose a fairly simple one. If you were the designer of the bridge, what element would you change to make it that bit easier to maintain?
I think one of the I'll do the political thing and not answer your question and tell you something else. But it's really important that people who have got experience in maintaining these bridges get involved in the design process, and it's not happening. It's not happening as far as you can see anywhere, and it's a pity, because it's all about access. We have made great strides in the UK. The Highways Agency issue their BDs to talk about integral bridges and this and that, but the bottom line is the guys designing in a design and build contract, who are engineers designing for the contractor, have got one thing in mind, and it's to win the bid. And that's right, because if they don't win the bid, that's it. That's their focus, and rightly it should be. It should be at the procurement side of things that the government or the agency who are procuring the bridge should make sure that that experience is there, because it's all about access. It is all about access and containment. And I think we continually underestimate how to get to places. And if I have to say, in Forth Road Bridge, I'll answer the question. Okay, in Forth Road Bridge, it's the joints. Anyone who's ever crossed over the bridge knows that every 18 metres they hit a joint, and those joints are half joints underneath. Forth Road Bridge, the deck actually doesn't act globally with the bridge as a whole. It acts separately. All it does is take the load. That deck itself it sits on stringer beams, or floor beams as the American calls them, longitudinal beams, which then sit in the big truss. And these beams are not not taken to contribute globally. All they do is take the load from the vehicles to the hangars and up to the cable. And what they did, to save a bit of money, because there's 4 of them in underneath one carriageway, 4 in the other, and there's 1.8 kilometres of them times 8. So even getting down a section size saved a lot of money. So what they did is they put a half joint in it and put a propped cantilever, and the half joints have worn out completely. And that's causing us major issues, and it's difficult. We can't do anything about it. It costs about 30 million to replace them all, and we don't even have a scheme to do it. We've tried a couple of things, and we're constantly going out every night and shimming them up, but it's only a temporary measure. So if there's anything, I'd do that. I have jokingly said that if we did anything in the bridge, it would be take the deck off and put a box girder on it. It would save a lot of problems. There's 200,000 square metres of painted surface in that truss. Trusses are great. They're great fun for an engineer, but they're really difficult to maintain. A box girder would be a lot easier. It would solve a lot of problems.
I just have a quick follow-up to that, which you may not want to answer, but just when they were going out to tender on the new Forth Bridge, did they approach, I suppose, the operators of the existing road bridge to input into the specification for the new Forth Bridge?
The official response from the government will be yes, they did.
Fair enough. Anybody else? Oh, sorry, Alex. Get you this.
On the replacement crossing, is there sensing equipment installed, and do you think that would be of any benefit?
Oh yeah, thousands of them. I thought there was only 1,000, but the guy who's installing them from Strainstall told me it's 2,000.
Okay.
We spend a lot of time repairing sensors, and there's definitely a place for structural health monitoring, and the best time to do it is when you're building the bridge, but it's what to do with the data that's the problem. And I'm not sure, the people who have put in the sensoring haven't really talked to the people who might be looking after it afterwards, and why you would possibly want some of it anyway. So.
Okay. And do you know what type of sensors they are?
Yep, there's they're putting in GNS or GPS. They've got some accelerometers, corrosion control on the piers. What else have they got? Accelerometers, GPS, corrosion monitors as well. I think that's probably the mainstay of it.
Yeah.
But there's also a big SCADA system for alarms, and there's anemometers and ice alerts as well in the carriageway. I think structural health monitoring certainly has a place, but it should never be thought of, despite what the manufacturers of all the gear say, it should never take the place of inspection. They both are complementary. But one of the issues the industry has is longevity of of the stuff. There's no point, and what do you do with the data? I went to see a bridge in Hong Kong, no, I wouldn't say Hong Kong, somewhere in the Far East, where they've got the model for the second crossing was put in, and there's a room where people were monitoring 24 hours the bridge moving, you know, and I thought, well, what are they getting out of this? It's great if something happens and you want to look at the data to see why did that happen, but for monitoring it on a daily basis or an hourly basis, I don't think there's many point to that.
Barry, first of all, thanks very much for a brilliant talk. And I suppose the question I have for you is, what does the future hold for the bridge? And as the years go by and the new structure takes most of the traffic away, will it be difficult to source funding to maintain the bridge?
That's an interesting question. Good question. The government have decided that the existing crossing will only take public transport after the new crossing's opened. The new crossing, we have 2 lanes going north and 2 lanes going south. And we've got 6 lanes going into it, both north and south. And every evening we see, and every morning, that 6 into 2 doesn't go, despite hoping that one day it might actually go, but it never does somehow. The new crossings only get 2 lanes north and 2 lanes south. And it's expected that our traffic is about 70,000 vehicles a day. The government figures are they're expecting 92,000 on the new crossing because it does attract traffic. Now, as our American friends would say, you do the math. I don't know how or what the public perception will be after spending £1 billion on a new crossing to be still queuing. Again, the government are saying that the new ITS system they've put in will help reduce these queues. But well, we'll see when that happens, whether it does or not. One of the problems is there's so many junctions at either side that the traffic doesn't really get a chance to, the ITS system doesn't get a chance to smooth out the traffic. So the new crossing is to take all general traffic, motorway traffic. The existing bridge is to take public transport only. So it'll go from 70,000 to 200 or so vehicles a day. The big problem is, and there is an issue because City of Edinburgh Council are against any additionality of road space at Queensferry. For their own reasons, they're concerned about congestion in the city. And you get this push-pull wherever you go from different sides of a river. Fife want the 2 bridges to be used in tandem. Edinburgh don't, I think is the general rule of things. Fife want it for expanding their economy, which is laggardly slowing behind Edinburgh's is buoyant and booming, and they supply the labour from the north side.
Paper there. The thing that struck me on it is 2004 when the first inspection was done. I mean, that's 40 years after construction. It's quite a long time before anyone had the will or the energy, if you like, to actually have a look at how this was performing. And I'm just wondering if, by the fact it was inspected in 2004, there's an assumption the defects were arising around 2004, but these could be historical defects, I wonder.
Yep,
from construction stage.
Yeah, I'm sure they are. In fact, there was a lot of discussion as to when's the start point. Is it when the wire is on the reel and leaving the factory? Is it when it just as the cable's wrapped? And there's 3 or 4 years there.
Yeah.
But I do remember in 2004 when we decided to open it up, some of our colleagues from the other bridges were asking the question, why are we doing this? There was quite a lot of questioning, and rightly so. You've not got any issues. It doesn't look as if it's having a problem. Severn Bridge has leaked water from the day it was opened. We haven't. So people were asking, why are you doing this? Why don't, and because in any operation you can't put the patient back to the condition it was. We could not restore the bridge, that cable, to its original compaction. Whatever you do, you're disturbing it. You're changing something. So and so those questions were rightly asked, but we decided that just to satisfy ourselves, we'd open up those two middle panels and have a look. 40 years, there was a lot of work being done in the 80s and the 90s in the States on this, but there was no guidelines on what to do. And Forth was considered, in American standards, as a young bridge, because some of their bridges are 100 years old.
And in terms of the location of the testing and the inspection and testing, it seemed it was at the lower end of the cable, which is probably the most convenient to actually do the inspection. I wonder, would that be more prone to corrosion because of the location, or did you inspect the cable further up the profile?
We did. We inspected at various locations. We inspected that panel there actually as well. That's another. We've got 3 different types of cable gantry stroke crawlers. That isn't suitable for inspection because you can't put a compactor and wrapper on it. You need a big chunky inspection platform for doing that. But that is great for dehumidification and for getting up and down the cable. So we've got quite a few of these. We've tried to flog a few of them as well, but no one seems to want them. We've kept a couple, but yes, we did look. We carried out a cable inspection to see if we could see any crossing wires, and we were aware that on Walt Whitman Bridge in the States, they found the worst panel was up here. Now it's a bit counterintuitive that well, water runs downhill, doesn't it? But sometimes it's the way the cable is compacted. If it's compacted uphill, you sometimes find there's water lying in these. So it's important that you look over a spread of the cable rather than just at the bottom, because the evidence has been that that's not the case. Unfortunately, it's on this tower here, on this side here. We've just started having a lot of activity. The dehumidification's now been running for a long time, and you saw the graph of how it's all looking great. We've just had a lot of activity recorded at that north tower in our acoustic monitoring system. We've had 7 wire breaks suddenly 3 weeks ago. Last week we had 3, exactly the same location, and we've had another one last night. It's quite worrying. What decided to do is put up a small access platform up the side of the cable. It's just at the point where the cable splays out over the tower saddle, so it's starting to lose its compacted shape, and there's a cowling over it at that end. Actually, you can't quite see there. You can see it there. That's the cowling. We're going to have to take this cowling off. We're going to support it on the hand strands with turfers and hopefully drop it open and have a look. But the problem is we've got to do all that, get that platform, winch it up there without disturbing or increase the risk unreasonably to these people here. That's one of the issues about these bridges, whether it's a suspension bridge or a cable stayed bridge, is that most of the difficult stuff is above the heads of the users. That's what makes them different from viaducts or beam and slab bridges. So the risk is always there. Every time you do something, you're increasing the risk to these people here, the users. And the difficulty is that society's attitude towards risk has changed significantly in 10 years. And we're constantly having to address that. What would be acceptable 10 years ago isn't acceptable now. So we have to be very mindful of that when we're doing the risk assessments. Because unfortunately, the ultimate arbiter of whether you're being reasonable or not is usually a man or a woman in a wig. And that's the difficulty. There are no rules written down on reasonableness. And I know that what we consider reasonable or unreasonable may be different from some of our colleagues, just because. And we've done things on the cable with a risk assessment, and we've had a contractor in, this contractor that's doing that, whose risk assessment might be different from ours. So it is difficult because most of the interesting stuff is above the heads of the people who are crossing the bridge.
Okay, maybe time for one more question if there's one. Yep, that's right.
You mentioned that you have 7 breaks in the last
Sure, recent past. Do you correlate those breaks or those incidents with you have the way in motion, and also your I assume you have monitors monitoring the wind speed. Is there any correlation between the loading, whether lateral or vertical, and the brakes, or are they just random?
We haven't managed to find anything yet. There does seem to be an issue in winter, and I think temperature's got something to do with it. There's still a lot of work needs to be done on why wires break, and the big issue at the moment is validation of acoustic monitoring, and we know that, as I said, if you put a bit of galvanised wire in that chamber with relative humidity less than 40, it will not corrode. But what happens to wires that are already corroded and have already got cracks in them? Our aim is to try and slow down the rate of deterioration. You can't make it any better, obviously, to slow down the rate of deterioration and to make it keep above a level where the bridge can operate for the remainder of its life. And I didn't answer that bit of the question actually, but that's the aim. And I'm fairly confident that the bridge will. Well, I was until I heard those 7 wire breaks actually. I was fairly confident up to that point that the bridge will have a service life for the rest, another 50 years, 75 years. I think it will be taking traffic over that time. We did look at replacing the cables, and that was one of the reasons. There was a big issue when the new crossing announcement was made. The Green Party and as a big Green lobby was saying we could replace the cables, and we carried out a study, and you can do it. The safest way to do it, eliminate risk to users, is to close the bridge for 3 years. But that's not possible politically, so you have to accept some risk. And what you have to do is build those towers up here, put a new saddle on, put a new cable in on there. Now you can imagine doing that while still having traffic running. It's not an easy task. It can be done, but there would be significant disruption. I think it would. We're in print to say it would be 122 million, but I think we dropped 100 million somewhere. I think it'd be about 200 million to do. And significant disruption, it would take 9 years. Significant disruption to traffic, and that was unacceptable as well. We ran a panoramics model on it, which is some kind of traffic magic thing, traffic engineering magic-y thing. It showed you these vehicles running across, and we were quite perplexed. We were running it for scenarios of traffic management for replacing the cables, and we wondered why there wasn't a queue northbound at PM. I realised they were still, 7 hours later, they were still stuck in the queue southbound. Getting into Edinburgh to come home. So the wee panoramics-y model-y things were still flashing away, going stuck southbound. Now it's not, life doesn't work like that. People would do something else, but the queues would have been horrific. So it wasn't acceptable to replace the cables, but there was a big lobby to do it. In fact, there's still people convinced that we were telling untruths in this and that you could do it without significant disruption. But you can't. The risks are too high.
You mentioned winter as a problem with maybe just with rain, the weight of water on the cables. I think I've seen a solution on some bridge in Southeast Asia where they put dimples on the skin of the cable where the water just fell down instead of falling as one all the way down. I think it helped a lot for weight, to reduce the weight.
Yeah, I think that would be wind-induced vibration on cable stays, which is a big problem. You get 2 droplets forming, and they do cause significant issues with stays on cables. You don't really have that on suspension bridges simply because of the size and the way the cable's tensioned. It's not a stay; it's suspended. But yeah, they do have that. One of the things that I've learned, and it's taken a while, that you can't keep water out of these things because they're too flexible. Unfortunately, some people still are painting cables, expecting that it's an answer. I'm afraid it's not. The answer is, and suspension bridges I think are still the preferred option for any span over 1,000 metres. I'm not sure why you would design a stayed bridge of over 1,000 metres, but you've got to have some certainty on the main cable, and if you fit a dehumidification system at the beginning when the wires haven't corroded, then I think that gives you the certainty, and that's the sort of message we're trying to get out. And I'm pleased to say that on the big bridges that have been built recently, Hardanger in Norway, Third Bosphorus and others in China, they've put in a dehumidification system right at the beginning. So the message is getting out. We're still to convince our colleagues in the States to do it, but hopefully we can.
Thanks very much, Barry. I'm just going to invite Eugene O'Brien to deliver the vote of thanks.
Thank you, Fergal. Thank you, Barry. It's a real pleasure to hear from the man who forced the British government to build a new bridge. Can't many of us claim that kind of power. It was great to see the historical and economic and social context that the development of cable-stayed bridges has been a part of. It was great to see this bridge in particular. I was delighted personally to see that that you have a site-specific traffic loading. It's good to know, and I'm sure it has saved you quite a bit of money, because what the code has is really just an approximation, as we all know. Dehumidification, as you've just said, it's a big game changer in this place. I think it puts cable-stayed bridges, or it puts suspension bridges back in the game again. It was looking as if they were on their way out.
Absolutely.
Everybody was worried about the cables. It's a little bit disturbing, to be honest, that we still need more research to understand hydrogen embrittlement, I think. That even if you have a functioning dehumidification system here, you still don't know for sure if the wire breaks are going to ever stop. And of course, it's a real game changer, because if they stop, well, then there's no engineering reason why you couldn't leave it open to traffic. And it becomes a political decision. And 8 lanes versus 4 lanes, it's a big difference. Very interesting that the approach spans was your biggest maintenance cost. I think there's a lesson in that one. And very interesting to see the new bridge. I think we're all excited to see a multi-span cable-supported, cable-stayed bridge. That's a very exciting one. Personally disappointed that there wasn't a site-specific load study, because my guess is that the probability of uneven loading between spans probably wasn't truly investigated well enough. Otherwise, you probably wouldn't have needed those crossing of cables, would be my guess. So anyway, it was a real pleasure, and I'm delighted to meet the man whose good night's sleep costs £3.5 million. And thank you very much on behalf of the 2 institutions.
Thank you.